So we're here to talk through this Kropki Fillomino puzzle by Prasanna. It has an almost symmetric theme. You see that except for missing a black circle in this edge, the rest of the Kropki clues are symmetric and all the numeric clues are symmetric. And getting full symmetry from a Kropki puzzle is somewhat challenging because the anti-rule of Kropki is to say where you don't see a circle is a pretty strong rule. And actually most of the logic we'll do in the solve, and something you should generally learn for approaching the Kropki style variation or even things like consecutive Sudoku style variations, is to think about how the absence of circles drives logic in different places. We'll see a similar path for the two corners, but I guess I'll start in this corner just because I think addition and subtraction by one is a little easier for people to think about. A key structure of clues is often this 2x2 square where the absence of the circle forces certain things about this chain. A lot of people sort of know this, but let's just view us as having some value x in the cell. The one right next to it is x plus 1 or x minus 1. The next one connected can continue in the same direction, so if we're adding one, we can add one again. They can come back to a central value or can become to an extreme. And then from these we can get to 4 potential values here, but the thing to notice is if x is ever in the cell, the only values that can be here are plus 1, minus 1. That would force a white circle to be present. And similarly, even if this is x plus 2 or x minus 2, if this goes and reverses, so if this was add 1, if this becomes a minus 1 and becomes x plus 1 again, there'd be a circle here. So what you really get is a chain that's going in the same direction around each of these spots, always increasing or always decreasing. And in this location over here, it'd be always multiplying, so times 2, times 2, times 2, or divide 2, divide 2, divide 2 as you go around. But you'll recognize you have to have extremes. So the first thing to recognize is you have to have extremes, and then the second is to recognize that cells like this will always have to be larger than 2. The smallest value in this grid could be a 1. We could have 1, 2, 3, 4, or we could have 1, 2, 3, 4, but this cell will always, at the very least, extend over one more cell. And similarly, this will extend over one more cell. The next thing to recognize is even if this is extending a few cells, and we're going to see this a whole lot in the puzzle as we go through the whole solve, is that we know the value next to it is 1 in any direction, which says that the opportunity for this cell to also occupy the cell above it isn't there, that we would need to see a circle marked next to it. And so the absence of a circle tells us that there's actually a hard border in this cell. And now we can pretty quickly get the exact value of this cell in both sides. It will use a similar kind of deduction. It either connects to this cell and is the same value as this cell, so in this case it would be a 3, in this case it would be a 4, or it can be its own hidden polyomino. In this case it would just be a 2 or a 2. Notice if it's a 2, we need a circle. If it's a 2, we need a black circle. Not the case, so the only possibility for these cells is for this to be a 3 in the lower right and all 4s in the upper left. We can now mark, although we don't know the exact spots, if this is a 2 versus a 4, and let me, just for a little cleanliness, keep the either or options going opposite. So there are 2 scenarios. It's either always the upper left digit and 2, 4, and 5 are used, or always the lower right digit and 1, 2, and 4 are used. Note that in either of the scenarios down here, this extends over one more cell. And now we should ask if in the case of this being a 4, does it have anywhere to go? It would be touching this 3. You need to have a circle in this or this cell. So in the lower right, we end up being able to set this whole cycle by looking at this cell and seeing it can't extend further. So this has to be a 2. This is the logic. And we can go further with this in a bit, but let's at least sort of see how it plays out in this side to similarly set the overall expectations. Again, the either or is what's in the upper left versus lower right. Whichever this is, this extends out one more. This cell can't come one over to the left. It's going to have to come out this way. So it's like this. If this is a 1, it doesn't have to extend further. If it's a 16, it has to come this way, but we shouldn't do too much with it from there. But what we can do is try to think about the value in this cell in the third row and second column. It's connected to these numbers, so it could be something in this range 1, 4, 16. Notice that we have to also deal with what's in this cell, and it can either be a 1 and not connect to anything down here, or it could be a 4. Well, actually that's an instant failure. Could it be a 16? If it's a 16 to a 16, what you'll end up seeing is that both of these digits are 8. You need another black circle here. And so the critical thing to deduce is that this is an isolated cell. It can't share anything in common with the cell beneath it. That lets us quickly eliminate the 1 as a choice here. It lets us eliminate the 2 as a choice because 1 can't touch to 2 without a Kropki white or black circle. And this is 8, 8, this is 16. These is 2, filling it out. We have a little time from which we can just use these 8 and 16 together to walk around the grid. They don't want to touch each other in the cell, so the 16 can't come down. Similarly, the 8 can't go to the right, so the 8 comes down 1. The 8 also can't then go immediately to the left because it would be touching a 4 or 16 cell. So what we see is a shape, and we'll see it again in the lower right as we get to it, where the digit that's here sort of makes this L. The 16 needs to still avoid the 8, so it comes this way. The cell is fully isolated now. This is a hard border, just as we saw before. The 8 can't come across, the 16 can't come down. So you get this shape starting. The 16 comes over like so. And there's one more spot we can look at in this corner before we'll need to come back to this side, and that's sort of dealing with this cell. As we've done before, it's already cell connected by a dot, but that now limits its ability to come straight down. You need to have another dot here, so this has to come like this. That immediately eliminates 4 as an option. It would touch the 4 Fillomino. And so this is how the side of the grid starts, and I guess I can write in these options. We actually don't know how they're tethered yet. So coming to this space, as we saw with the 8, the critical next step, it can't come to the right. It's going to need a circle to touch this. 3, so it comes up. It can't come immediately over. That would touch this 5. So it's going to come like this. The white circle here is a 3 or 5, but that means the 4 can't come over one more cell. It would need a white circle there. So just as we saw an L shape for these initial cells, we see this L shape. The 5 acts much like the 16 above and needs to dodge the 4, isolating the cell, and then it dodges again here, and it completes like so. This 3 or 5 can't come immediately up or down. It would touch a 4 and need another cell, so it comes over. If it's a 3, it's going to have to come up this way. If it's a 5, it's going to also have to come up this way. But you now have an awkward space where we have 2 cells down here. If it is a 2, it's touching a 4 and 3, which is a double no-no. There need to be a black circle or 2 white circles to do that. So this kind of needs to at least take 1 more cell. The only way that happens if it's a 5, and if it is a 5, this is the way it has to play out. Again, dodging cells where you need to see a circle and don't have a circle. This is a 3, 5. This, extending as we've done before, could be 2, 4, or 6. 2 is an instant failure. We need a circle to be a multiple of 2 here. 4 can't touch 4. Already finished this Fillomino, so this is a 6. That tells us this is a 5. It's going to dodge the other 5. The 6 is going to come out like this. The 6 isn't going to come further down this way. It's going to have to touch a 5 if it does so. So it's going to sit like up here. I think we'll want to do a little more in this corner before we come over. So let's come to an interesting cell like this. And we'll actually have a similarly interesting cell up here. The reason these are interesting is the 3 itself can't occupy it, but now we have a cell. It's part of a hidden polyomino. We don't know what number it is, but it actually has it has a lot of numbers that are low that are eliminated from it. It can't be a 1. It's next to a 2 already. It can't be a 2 or 3, it's touching those. It can't be a 4, so this has to be 5 or larger. So what you'll see is you have a polyomino of unknown size that's growing over in this direction. It becomes quickly connected to the given 16, and that fills out this space like so. Up here, we similarly will end up seeing that this can't be a 1, it can't be a 2, it can't be a 3. It's touching a 2, so it also can't be a 4. There needs to be a black circle here, so this is also 5 plus. And we'll get back to that in a bit. What we should try to do, though, is finish out what's going on in this space with this 8 and other clue. We actually didn't know when we first wrote this 16 if this could be an 8 or a 32, but there's just no room in this grid for a 32 clue to live, so it's really going to need to be this. This 6 polyomino that's starting to grow can't come back and reach over to itself because this is a 5 or 7. We can actually see once we put in this 8 that if it's a 7, the 7's going to touch it, and that's going to be an issue. So we actually are building something like this. And so this 6 has no option but to come over in this shape. This gives us the last digits for the 8. Let's deal with the left side and finish out this large 16. It needs to at least take these cells to be able to fill the space. We can put up that the 4 at least takes 1 cell there. It looks like 5, 10, 13 cells have been filled for the 16. We need to have at most 3 more to place. If this cell here were a 16, 1, 2, 3, 4 to connect back, that's too many cells. So it looks like it's going to be a 4 that finishes off this 4. It's a 16, 16. This cell can't be a 16. We have 1 more cell to place for the 16, and so this finishes like this. This 5, if it grabbed the cell, could not take another cell without growing too large, so it's going to have to take 1 of these cells to finish. I think there's a set of tricky steps to do the end up here, but the first thing that helped me was to see an issue of taking this cell, at least behind 2. The 2 is touching to a 4, and there's no circle here, so there's this is either going to be a 1 or a very large number, and the reason is it can't be 2, can't be 3, can't be 4, can't be 5, can't be 6. This is 1 or 7 and above, and that tells us something about this. This can't be 1, but this is sort of 7 and above or something larger. So long or short of it is you can force this form of the 5 to sit up here. We can now do a little bit of counting around the 16, which can't take this cell. It has 5 up here, max to 10 to the cell. This would be 11, 12, 13. 2 more cells have to belong to the 3 up here, so this would have to take 14, 15, 16 to get to here. Counting for all the cells we know up there. If we stopped at just the 16 and left 2 behind, we'd have an issue. So this has to take 1 more. That count of 16 requires getting several more cells up here, so this sense of 5 plus, well, again, we can see that for us to work at all has to be another 16, and there's at least 1 cell of these that connects us together. So let's do a count of what we've got. We have 14 plus a 15th cell here. We're going to take 1 more cell as a 16, we're going to use a 3, and we're going to have an isolated 1 as the n. So let's start in this corner. It can't be a 1, it can't be a 2, it could be part of the 16, but counting for the cell would be 17 total. So the only way the cell sits is as part of the 3 polyomino. We now need to take 1 more cell overall. We're going to leave 2 behind. If we left 2 up here, that would force taking this cell. You'd have a 2 sitting next to these groups, so that's bad. So we're going to take 2 of these cells. We can't take this cell. The remaining cell will be a single 1, as we marked before. Can't be there, can't be there. The 1 has to be here. Mark 16, 16, and we're finished with the puzzle. As we said at the start, it's pretty elegant. The design, while it doesn't have absolute symmetry, It has a lot of symmetrical aspects to its logical solve, and then still has some pretty good challenges of packing these larger polyominoes in. The way that the shapes dodge each other in similar ways is sort of something that Prasanna highlighted quite well in the solve, and hope that you learned something through this tutorial about Kropki puzzles in general, and be able to apply some of these lessons in the future. So thanks, and we hope to see you again soon.